All right, let's introduce Legendre polynomials. They have some really amazing properties. They come from solutions to the Legendre equation. So the Legendre equation is as follows. I can write it as the derivative of 1 minus x squared times y prime equals negative k times k plus 1 y. And here I'm assuming that k is a non-negative integer. So k could be 0, 1, 2, some non-negative integer. This is the Legendre equation. It's a differential equation. I wrote it in this form because it's useful to have this form when we want to understand properties of the Legendre polynomial, but this form of the Legendre equation isn't my favorite for actually finding solutions. You can rewrite the Legendre equation by taking this term on the left and differentiating using the product rule. So equivalently, this Legendre equation is the same as 1 minus x squared y double prime, I'm taking the product rule here, minus 2xy prime. Then I'm going to add this term on both sides to get plus k plus 1 y equals 0. So this is the form of the Legendre equation that I'd like to solve. We have an approach to solve these types of differential equations using series. So to solve, I'm going to assume that I have a solution of the form, the sum going from 0 to infinity of an x to the n power. The approach is to take this expression, find the derivative and the second derivative, and then plug it into the differential equation to find a relationship between the coefficients in the series. Here's how that looks. So then, when we actually plug in this form of y into the differential equation, we get 1 times the second derivative, and the second derivative can be written as the sum going from 0 to infinity, an plus 2, n plus 2 times n plus 1, x to the n, minus x squared times the second derivative would give me the sum going from 0 to infinity, this time n minus 1 x to the n. That's x squared times the second derivative. Then minus 2x. So minus 2 times the sum, n going from 0 to infinity. N times n, x to the n. And lastly, I have this term with the k's, k plus 1, the sum, n going from 0 to infinity, of an x to the n. All of that should equal 0. Now, the coefficients of x to the n on both sides of this equation have to equal the coefficients of x to the n on the right side of the equation. But there are no x to the n's on the right side of the equation, it's just 0. So everything that I've underlined in red, with this minus sign, a 2 of course, everything underlined in red has to equal 0. So I can compare the coefficients of x to the n on both sides and get a big equation involving an plus 2 and an's, setting that equal to 0. This, after solving, so solving for an plus 2 gives the following interesting relationship. An plus 2 is equal to n times n plus 1 minus k times k plus 1, all divided by n plus 2 times n plus 1 an. This is a fundamental relationship between the coefficients in the series solution to the Legendre equation. Now, what's interesting about this is that k is a non-negative integer. K could be 2, for example. Then when n happens to be the same value as k, so when n and k are the same, look at the numerator here. If n and k are the same, then the numerator is 0. What that means is that when you write down the series solutions to the differential equation using this fact, one of the terms will eventually be finite. So one of the infinite sums that you get when you solve this differential equation is not an infinite sum after all. It's really just a polynomial, a finite sum. Again, the reason is because eventually these terms will all be 0 when k and n match. This is a little abstract, and we'll definitely do an example in a minute. But before I do, I'd like to define what the Legendre polynomial actually is. So, define the Legendre polynomial we're going to denote it by p subscript k of x. So we're defining the Legendre polynomial to be the polynomial solution to the Legendre equation such that pk of 1 is equal to 1. And I'll discuss why we have this last condition in a second. But this is the definition of the Legendre polynomial. It's the solution to this differential equation that's actually a polynomial. So I'd like to end this video by actually calculating one of those Legendre polynomials, and then I think in the next video I'll calculate a bunch more. So here is the example. How about let's find the Legendre polynomial p2x. What is the second Legendre polynomial? So here is the idea. I've already done the work up here. This boxed relationship between the coefficients in the power series, I can record in a table. So here's my table. And in the table, I'm going to have different values of n. And an plus 2 equaling n plus 1 minus k plus 1, all over n plus 2 times n plus 1, an. All right, so n might be 0, 1, 2, 3, 4, and so on. Now, if n is 0, I plug in 0 for n here, and I find that a2, here, k is equal to 2. So not only am I plugging in n equals 0, k is 2. So if n is 0, this is 0, and k is 2, then I get negative 2 times 3 over 2. So I think I get negative 3 a0. If n is equal to 1, then I get a3 is equal to 2 minus 6 over 2 times 3. That's times a1. Now here's where the magic happens. When n is equal to 2, since I'm taking k equals 2, n and k match. That makes this term equal 0. The n equals 3 case, I will get a5 is something. I actually don't care about what that is, because the observation is every even coefficient after this point is 0. Why? a6 is some constant times a4. Now a4 we've already decided was equal to 0. So that's 0. a7 is going to be some constant, some number I don't really care about right now. But a8 is also 0. So therefore, the solutions to the Legendre equation are y is a0 plus a1x plus a2x squared plus a3x to the third, and so on. That's my full series solution. That's everything written out. But now, since I know information here, I have n equals, so a0 I don't know, a1 I don't know, but a2 I know is negative 3a0x squared. a3 is some constant. It involves a1, so I'll write that in, I guess. So I get negative 4 over 2 times 3 a1x cubed. a4 is 0. So there's no a4 term. a5 is going to involve a3, which involves a1. So what I'm saying is this. I have two linearly independent solutions to the Legendre equation. My first solution is a0 times 1 minus 3x squared. My second solution has a coefficient a1, and then I get x minus 4 over 2 times 3x cubed, plus an infinite number of terms that continue here. This is the finite polynomial solution. It's almost the Legendre polynomial. The only problem is I need to decide what constant a0 to put in front here. What constant do I need? That's when this second condition comes into play. I need to pick the constant a0 to force this to happen. When I plug in x equals 1 into this polynomial, I want to get out 1. Right now, when I plug in x equals 1 just to the circled part without a0, when I plug in x equals 1 here, I get negative 2. So that means if I want to get out 1, I need to divide by negative 2. Therefore, the conclusion is this. Thus, the Legendre polynomial P2x is equal to, let me make some space here, is equal to negative 1/2 1 minus 3x squared. All right. In the next video, I'm going to find another Legendre polynomial or two. But again, to recap what happened, we have this certain differential equation. You can solve it with a series. When you solve it with a series, you get this relationship. When n and k are the same, eventually one of the terms will be a polynomial, not an infinite sum. That polynomial is what we're calling the Legendre polynomial, and we select the constant in front to satisfy this condition. Okay, wonderful. See me for our next video.